Now the next mode of heat transfer, which is convection. So in fact convection takes place when a fluid flows over a solid surface, when a liquid or a gas flows over a solid surface. It is in fact the mode of energy transfer between a solid surface and the adjacent fluid which is in motion. So the fluid would be in motion and it would be flowing over the solid surface. That would make it the case of convection heat transfer. And in fact the convection heat transfer involves the combined effects of conduction and the bulk fluid motion So what happens is that if we have a plate, a surface over which a fluid is flowing, so that would make it the case of convection heat transfer. So while suppose that the temperature of the surface Ts is greater than the temperature of the fluid. If Ts is greater than T infinity, so the heat would be transferred from the plate to the fluid and vice versa. So when the heat would be transferred from the plate to the fluid, so there would be the diffusion of the molecules. The heat will be transferred due to the diffusion of molecules, due to the movement of the molecules, due to the interaction of the molecules. And what will happen is that when the fluid would come over this surface and it will get heated up, so the fluid is constantly in motion. So it will get heated up and it will be pushed further by the upstream fluid. And this upstream fluid will take its place and it will then get heated up. It will get heated up and then it will be pushed downwards, downstream, and then the fluid will keep on replacing. So what is happening is that along with the conduction, there is fluid motion as well. Which is causing more heat transfer. So the combination of the two is what we call convection. Or we can say that convection is the mechanism of heat transfer through a fluid in the presence of bulk fluid motion. That is the same definition as the previous one. So what happens is that in fact the fluid which is flowing over this surface is composed of infinite number of layers. Let's say the first layer, and then the second layer, and then the third layer, and so on, right? And then so on. So of course those layers would not be that far apart, but I have only made them far apart for illustration purposes. Now suppose that the plate is at rest. So the very first layer of the fluid which is in direct contact with the surface would be having the same velocity as that of the surface. So if the surface is at rest, this very first layer of the fluid which is in direct contact with the surface would also be at rest. This is what we call no slip condition. And then the second layer, so the velocity of the first layer of the fluid would in fact be zero if the plate is stationary, if the surface is stationary. Surface is this black surface. Now the first layer would be having the same velocity as that of the surface. If the plate is at rest, the first layer of the fluid will also be at rest, and the second layer of the fluid will have a velocity greater than zero. And it may have a velocity of, for example, 0.5 meters per second. You may assume it as 0.5 meters per second. And then the third layer, if I call it the first layer and if I call it the the second layer, and if I call it the third layer, and so on. So the third layer would have a velocity greater than 0.5. So what is happening is that as we are moving far away from the plate, the effects of the plate are being minimized. The effects of the plate will not be that strong if we are far from the plate. The closer we are to the plate, the effects of the plate would be felt strongly. So 0 meters per second, and then 0.5 meters per second, and then 1 meters per second, and then the fourth layer would be having 1.5 meters per second, and so on, till we reach a point where the effects of the plate will not be felt at all. Right? So if, let's say, if this free stream velocity, we call it u naught, right? U naught, or we also call it u infinity. So if the free stream velocity is suppose 10 meters per second, so what will happen is that the velocity will of the fluid layers, velocities of the various fluid layers will change from 0 to 0.5 to 1 to 1.5 to 3, 4, 5, 6, and then ultimately it will reach this u infinity. Ultimately it will reach 10 meters per second, if we assume u infinity as 10 meters per second. It means that there is a region where the effects of the plate, where the effects of this surface, where the effects of this plate, it may be a plate, it may be a cylinder or anything, for the time being we are calling it a plate, where the effects of, means if this is that region where the effects of the surface are being felt, and outside this region the effects of this surface will not be felt. So this region is what we call boundary layer. This region is what we call boundary layer. Now this boundary layer is called velocity boundary layer. Why do we call it velocity boundary layer? Because this is the region where we are considering the changes in the velocities, where we are considering the changes in the velocity of the fluid, or velocities of the different layers of fluid. So you can, I have just mentioned that if we go far away from the plate, the effects of the existence of the plate will be minimized, and the velocity will keep on increasing from 0 to 0.5 to 1 to 1.5 to 2 to 3 meters per second to 5, and then ultimately it will reach about 10 meters per second if we consider this u naught as 10 meters per second. So if we are moving away from the plate, then the velocities of the layers of the fluids will keep on increasing. Means if we move in y direction, if we call this y direction, right? So if we are moving in y direction, then the velocities will change in y. The velocity will change in y. So this is what is shown over here. This is what is shown over here in this velocity profile. This is what we call velocity profile. So you can see that it is uy. Uy means u as a function of y, or u in y direction. U in y direction. The velocity in y direction. So over here you can see that the velocity is negligible, and then the velocities start increasing. Right? The velocity increases because and then the velocity increases further, and then ultimately it will attain u infinity of 10 meters per second. How do we see that the velocities are increasing? That would be indicated by the length of those arrows. Over here the length of the arrow is smaller. Over here it increases by a certain amount, and then it increases further, and then it increases further. So in fact the length of the arrows are in fact representing the values of the velocities. A smaller arrow means a smaller velocity, a larger arrow length means higher velocities. So Uh, so velocities are in fact increasing in y direction. Velocities are in fact increasing in y direction means that when we are moving away from the plate, the velocities are increasing, and ultimately the velocity will become 10 meters per second, or the free stream velocity, or the free stream velocity. So this is the velocity profile, and this region is the boundary layer. So the velocity profile is only just like temperature profile, is telling us the variation of velocity in y, is telling us the variation of velocity in this direction, in y direction. Now I was just telling you that the fluid is composed of infinite number of layers, 1, 2, 3, so on up to 100, 200, and so on. Now let's talk about the heat transfer. Now what will happen is that the first layer, which is in direct contact with the surface, would have the same velocity as that of the surface, and if the surface is not moving, if it is at rest, the that first layer would also be at rest. Now if we consider this Ts to be, suppose, 100 degrees Celsius, if we consider this Ts temperature of the surface to be as 100 degree Celsius, and if we consider the fluid at that was 10 meters per second, and if we consider T infinity means the temperature of the free stream, fluid. If we consider the fluid to be at let's say 30 degrees Celsius, so what will happen is that the heat will be transferred from the surface to the fluid, from higher temperature of 100 degrees Celsius to a lower temperature of 30 degrees Celsius. So since the relative velocity between the plate and the first layer of fluid, since the relative velocity between the plate and the first layer of fluid is 0, so the energy would be transferred via pure conduction, and then there is some relative velocity between the first layer and the second layer, because second layer is moving faster than the first layer, and there is relative velocity between the second layer and third layer, because third layer is moving a little bit faster than the second layer, right? So there would be energy transfer due to molecular diffusion. The molecules would be going here and there. Of course, this is the usual mode of heat transfer. But what will happen is that since the fluid is in motion, it is moving with an aggregate velocity of 10 meters per second. An aggregate velocity of 10 meters per second. So the fluid, the upstream fluid is in fact pushing this fluid downstream. So the fluid will get heated up, and then it will be pushed by the upstream fluid to a downstream position, and it will be replaced. This fluid will be replaced by a colder fluid, you can say, right? So or a relatively colder fluid. So it would be so there is the energy transfer due to the molecular diffusion, and then it is being supplemented by, it is being enhanced by, or it is being supplemented by the bulk fluid motion. So this combined effect of heat transfer is called convection. This is what is meant by combined effects of conduction combined effects of conduction and the bulk fluid motion. Right. So coming back, so the layer of the fluid which is adjacent to 100 would be having a temperature around 100, right? And then the temperature will continuously keep on decreasing, because what will happen is that the temperature of the free stream fluid is 30 degrees Celsius. The temperature of the free stream fluid is 30 degrees Celsius. So outside over here in this region, the fluid is having a temperature of 30 degrees Celsius, means outside the boundary layer. Just like we have a hydrodynamic boundary layer, just like we have a velocity boundary layer, we do have a thermal boundary layer as well. So what was the velocity boundary layer or hydrodynamic boundary layer? That was the region where there was a variation in velocity in y direction, right? The velocity boundary layer over here, we are only being shown the velocity boundary layer. We are not being shown the temperature boundary layer, but that is fine. So the velocity boundary layer is that region where where we will see the effects of the variation of the velocities, right? If we are moving away from the plate, the velocities of the layers of the fluids will keep on increasing till we reach the free stream velocity of 10 meters per second or whatever it is. Similarly, there would be a thermal boundary layer. Over the thermal boundary layer and the velocity boundary layer may overlap each other, or they may have different thicknesses. The velocity boundary layer may be thicker at any x. For example, over here, the velocity boundary layer may be thicker than thermal boundary layer. It means that if we consider this position x1, so what will happen is that the velocity boundary layer is having this much of thickness. So the thermal boundary layer would be less than that. So the thermal boundary layer would end somewhere over here at this x, and it may be the other way around. For example, at any particular location, at any particular x, the thermal boundary layer may have more thickness than the velocity boundary layer. In fact, that depends upon the fluid. That what type of the fluid do we have? Is it a gas? Is it air? Or is it liquid metal? It depends upon that thing. We will inshallah discuss it when we would start convection in detail in chapter 6. So the first layer of the fluid, which is in direct contact with the surface, would have a temperature of around of almost 100 degrees Celsius, and then the second layer, which is farther from 100 degrees Celsius, which is farther from the plate, would have a temperature, let's say 99 degrees Celsius, and then the third layer would have even a lower temperature, let's say 98 degrees Celsius, and then 97, and then 96, and then 90, and then 80, and then 50, and then 40, and then ultimately it will reach the free stream temperature of 30 degrees Celsius. So there would be a temperature, there would be a region. This is the region where the effects of the plate, where the effects of the temperature of the plate on the fluid are being felt. So that would give rise to a thermal boundary layer region. Over here, we are not being shown the thermal boundary layer, but we will see it in a bit. So, but you should be able to figure it out that if we are moving away from the plate, when we are moving away from the plate in y direction, the velocities are increasing. Right? So this velocity profile is made in this way, such that the lengths of the arrows, which are in fact representing the magnitudes of the velocities, are increasing. But if we think of how would the temperature profile would look like, so you should be able to figure it out that the temperature, what is happening with the temperatures. Temperatures are constantly decreasing. So what should happen is that the length of the arrows when we move away from the plate, so the length of the arrows should decrease. So we will see it in a bit. Or if I have it, yes. So this is how the temperature profile would look like if T is greater than, if TS is greater than T infinity or T naught. We usually call it T infinity. So see what is happening with the temperature profile. The lengths of the arrows are constantly decreasing. Is for the same reason that I have mentioned, right? And then there would come a point where the temperature of a certain layer of fluid would approach T naught or would approach T infinity. So that layer, that region would be termed as, this region would be termed as thermal boundary layer. Over here you can see that the velocity boundary layer is thicker than the thermal boundary layer. It may be the other way around. For example, the temperature boundary layer may be thicker than the velocity boundary layer, or they may have almost the same thicknesses at any x. So this is the temperature profile. When Ts is greater than T infinity. It means that the fluid is being heated up. However, if Ts is less than T infinity, so what will happen is that the heat will flow from the fluid to the surface. If Ts is less than T infinity, so ultimately the heat will flow from higher temperature fluid to the lower temperature surface. So what will happen in that case? If the temperature of the fluid is more and if the temperature of the surface is less, so let's say if the temperature of the fluid is 60 degrees Celsius and the temperature of the plate is 20 degrees Celsius, so what will happen is that the temperature of different layers of fluid will continuously decline from 60 to 50 to 40 and then to 30. So the temperature profile in that case would not be having this shape, would not be having a continuously declining trend. Rather, it would take this shape, right? Because now consider that this is not velocity, but this is temperature. For the time being, consider that this is not velocity, but this is temperature. So over here the temperatures are higher, and as we move closer to the plate, the temperatures would be lower, right? So this is eventually the case where T infinity is greater than Ts. If T infinity is 60 degrees Celsius, we would be having higher temperature in this region, and Ts is ultimately 30 degrees Celsius. So the temperature would continuously keep on decreasing from 60 degrees Celsius higher temperature to a lower temperature of 30 degrees Celsius or Ts. So the temperature profile may take this shape, or it may be the opposite shape, depending upon whether Ts is greater than T infinity or Ts is less than T infinity. Okay. Now, in the absence of any bulk fluid motion, means if the fluid is not moving, so the heat transfer between a solid surface and the adjacent fluid would be by pure conduction. If the fluid is not moving, so there is no bulk fluid motion. So all the heat transfer would be via pure conduction. So what happens is that the presence of the bulk fluid motion enhances the heat transfer between the solid surface and the fluid. How? It pushes it, and then the fluid is getting heated up and is being replaced. So the heat transfer is in fact being enhanced, is in fact being increased by the bulk fluid motion, which is in fact in convection. Over here it says the convection heat transfer involves fluid motion as well as heat conduction. Right? The same thing as we have been discussing over there on the top. the fluid motion enhances the heat transfer. And how does it enhance heat transfer? What I have just explained is that it brings the hotter and cooler chunks of fluid into contact, thus initiating higher rates of conduction at a greater number of sites in a fluid. This is how the convection heat transfer in fact enhances, increases the heat transfer. The convection mode in fact increases the heat transfer rate. It increases the energy transfer rate. So therefore, in case of convection, total heat transfer is due to the superposition, or you can say the addition, of energy transferred by the random motion of the molecules, means the diffusion, right, and the bulk fluid motion. Now, there are two terms that we should be looking at. We have discussed convection, but there is another term which we call advection. What is advection? Advection refers to the transport due to the bulk fluid motion only. Due to the bulk fluid motion only. So that would be the energy transport. Transport means energy transport, energy transfer. So advection refers to the energy transport due to the bulk fluid motion only. However, if we consider the combined effects of bulk fluid motion and conduction, diffusion, we call it convection. So you can say that convection is advection plus conduction or diffusion. So this is what we have discussed. We have taken a look at those slides in which there we have seen the velocity profile and a temperature profile. Profiles very simply mean the variation of the parameters such as velocity and temperature when we move far away from the plate. And we have seen over here that the two boundary layers may have different lengths or they may have the same lengths. This is a good diagram in the sense that it is explaining first of all the no slip condition that I had just explained a little earlier, that the velocity is zero at the surface, which is what we call the no slip condition. So the velocity of the fluid which is in direct contact with the surface, so the relative velocity between the two would be zero, and this is what we call the no slip condition. And the heat transfer will take place from the surface to the very first layer of the fluid via pure conduction, and then it would be conduction augmented by or supplemented by the bulk fluid motion, which we call convection. So over here you can see the length of the arrows. See the shortest arrow, and then larger arrow, and then larger, and a bit larger, and then a bit larger, and then you can see that those four arrows have got the same length. So it means that we have got the free stream velocity. That we have got the free stream velocity means the velocity is not changing beyond this point. The velocity is not changing in y direction beyond this point, and this region is therefore called the boundary layer. In fact, the velocity boundary layer, because we are considering the velocity over here, and same is the case for temperatures. However, over here there is a discussion between a laminar boundary layer and the turbulent boundary layer. I would suggest you that we keep this discussion for chapter number 6, because we would be discussing the laminar and turbulent boundary layers in chapter number 6 in a lot of detail, because that is the case where we would be learning convection in detail. Courtesy goes to NASA. Now there are various types of convection. For example, there is a natural convection, and then there is a forced convection, and then there is an external and internal convection. When the fluid is flowing over a surface, for example, when the fluid is flowing over a plate, so that is sort of external convection. However, if the fluid is flowing inside a pipe, we call it internal convection. And if the fluid is flowing outside a pipe, over a pipe, then we call it external convection. And natural convection and forced convection. And the forced convection is that convection where the fluid is forced to flow over a surface by some external means such as a pump or a fan. Let me give you a very simple example. Suppose you are playing cricket or football outside, so you get sweated, right? So let's say after the game is over, and then you are standing on the ground or near your house, and then your sweat would get soaked. So that is, consider it as case A, and consider case B as a case where in order to soak the sweat, you go and stand in front of a fan, right? So what will happen is that, and then you realize that when you stand in front of a fan, the sweat will go away much quicker. Right? It will go away in a less amount of time, quickly. So what is happening is that when we are standing in front of a fan, the fan is making the air flow over our body with a larger velocity. So in fact, we are using that fan. So as to make the air, so as to make the fluid means, so as to make the air flow over our body with a higher velocity. So that will increase. So what is happening in fact is that the bulk fluid motion is increasing. In fact, with the increase in velocity, the bulk fluid motion is increasing, which will in fact increase the convection heat transfer rate. So the forced convection would result in higher heat transfer rates as compared to natural convection. Convection heat transfer depends upon a lot of parameters, such as fluid velocity. As I have just explained over here, that the larger the fluid velocity, more would be the convection heat transfer rates, and the fluid properties as well, such as viscosity, thermal conductivity, density, specific heat, and the fluid velocity, which we have discussed over here. So let me give you a very simple example that how does it depend upon thermal conductivity. See the fluid is flowing over the surface, right? And let's say the Ts is greater than T infinity. So the heat will be transferred from the surface to the fluid, right? Suppose that the fluid which is moving is air. Now air has got a low value of K, as we were discussing in one of our previous sessions, that the value of K, thermal conductivity for air, is 0.0 something, right? So in this case, since the air has got a very low value of thermal conductivity, so the heat will not be conducted to air that easily. So since the air is not a good conductor of energy, is not a good conductor of heat, so it will not take away the heat that easily, or that quickly, or that efficiently. However, if we have, for example, a molten metal flowing over the surface, and that molten metal, of course, that is a metal, would have a very high value of thermal conductivity. For example, if you recall, or if you go back and refer, the value of thermal conductivity for copper was about 400 watts per meter Kelvin, right? So if we have a molten metal which is flowing over a surface, so that would have much higher thermal conductivities in the range of 300 or 400 or 200, and those values of thermal conductivities are much higher as compared to the conductivities of air. So they have got the ability to conduct heat. So they would be able to take away more energy from the heated surface. So this is how the convection heat transfer would depend upon the thermal conductivity, and of course it would depend upon the viscosity as well, for the very obvious reasons, and you can refer to the book for further discussion. This is the illustration of convection. Over here we can see that if we are heating the water, right, on a stove, this is the electric stove. The stove may be electric or it may be the fire stove. So if the water is getting heated up, so then the water will get heated up and it will move in the upward direction, and then it will be replaced by the cold water. See, it is going up. The red is going up and the blue is coming down. The red is going up and the blue is coming down. It means that when the water would get heated up, so it would become lighter because of the density difference. And you would have seen that in one of the previous definitions of convection where we were discussing convection. So it would get heated up and it would become lighter, and then it will rise upwards, and then its position will be taken by the colder fluid. So this is what we call convection currents. This is what we call convection currents, where the warmer water will rise and the cooler water will descend. There are radiation effects as well, but we will discuss radiation when we will come on to radiation. This is another illustration where the air which will get heated up by the ground via conduction will move further upwards via convection. And how the ground is heated up? By the solar radiation. So we will discuss radiation when we will come on to the topic of radiation. Now that is the same thing that we have discussed before. This is the velocity profile. This is the velocity profile, where the velocity is increasing from 0 to the free stream velocity. So 0 velocity, 1 meters per second, 2 meters per second, 3, 4, 5, 6, and then ultimately to 10 meters per second if it is 10 meters per second. And you can see that this is the hot block. So this surface Ts has got a temperature more than T infinity. So if Ts is greater than T infinity, so as we have discussed previously, this is how the temperature profile will look like. It will continuously decrease from a higher value of Ts to a lower value of T infinity. In fact, this is the temperature variation of air. It is the temperature variation of air in y direction. In y direction, as we move away from the surface, hot surface. Now, this is the same velocity boundary which we were discussing. So you can see that there is u infinity, the free stream velocity, and as soon as it flows over the surface. See, if there is no surface, what will happen? If there is no surface, then the fluid will keep on moving with the free stream velocity of 10 meters per second. So there would not be any boundary layers, there would not be any variation in velocity. So this disturbance will only be created by the existence of the surface. So the boundary layer will start originating only from the point where the plate starts at. Right? And then we will have this velocity profile where the velocity will keep on increasing from 0 to the value of u infinity ultimately. There is also being shown shear stress. Of course, you know that between the two layers of fluids there would be shear stress, and this is being shown over here. However, we will refer to the expression of shear stress in chapter number 6 inshallah. and this region is the region where the effects of the plate are being felt on the velocity of the fluid. So this is called the velocity boundary layer, and the thickness of the velocity boundary layer is being represented by delta. And since the delta grows in x, the delta increases in x, so therefore it is being represented by a delta x. Delta x means the delta at a particular x, because over here at this x delta has got some smaller value, whereas over here delta has got some larger value, because the boundary layer will grow as the fluid will flow over the surface. This is an important discussion. It is not difficult at all, but however you must know it, that the thickness of the boundary layer is the value of y. Isn't it the value of y? The thickness of the boundary layer is the value of y, right? Because the boundary layer is growing in y direction, right? For which the velocity is approximately 99% of u infinity. Is approximately 99% of u infinity. So what is after 99% of u infinity? 100% of u infinity means u infinity. So if the velocity is less than u infinity, we call that region as velocity boundary layer, right? So velocity will increase from 0 at this interface to what will be the velocity over here? Over here the velocity would be about 99% of u infinity. This is what is written over here. U means the velocity at any point. Velocity over here, the velocity over here, the velocity over here, the velocity over here, and the velocity over here. So u is in fact uy. U is in fact uy. Velocity at any y. So what will happen after 0.99 u infinity? It would be 1 u infinity. It means that when u is the same as u infinity, the boundary layer has ended. The boundary layer has ended. So there is a region where the effects of the plate are being felt, which we call velocity boundary layer, and after the boundary layer we would have the free stream conditions, free stream velocity, free stream temperature, and so on. Now the thermal boundary layer. I think we have discussed it, right? So there is no point in discussing it again. The fluid is moving with a free stream temperature of T infinity, right? And there would be a Ts, and if Ts is greater than T infinity, you can guess whether Ts is greater than T infinity or not by looking at the temperature profile, right? So what is happening is that the temperatures are higher over here near the plate, and then the temperature reduces to T infinity, because the length of the arrow is, or the length of the line is more in this region, and the length of the arrow or the length of the line is smaller in this region. It means that T is decreasing from a higher value to a lower value. It means that Ts is greater than T infinity, and the fluid is getting heated up, so this is the region where the effects of the temperature of the plate are being felt. So this is the region what we call the thermal boundary layer, and after the thermal boundary layer the temperature would be the same as the free stream temperature, right? The temperature would be the same as the free stream temperature. After the velocity boundary layer ends, the velocity would be the same as the free stream velocity. So u would be the same as u infinity. Over here, when the thermal boundary layer ends, the temperature of the fluid would become the same as the free stream temperature, means that the temperature would become the same as T infinity. The thickness of the thermal boundary layer, just to differentiate it from the velocity boundary layer, is denoted by del T. Over here it was del, or you can write it as delta V for velocity boundary layer thickness, and then you can write delta T for thermal boundary layer thickness, and again delta Tx, because the boundary layer grows in x. Let's take a look at this thing. The thermal boundary layer thickness, delta T, is the value of y. Delta T is in fact the value of y for which this ratio, Ts minus T over Ts minus T infinity is approximately 0.99, is approximately 99%. See, see that if Ts is approximately what are the parameters in here? We have got a T, we have got a Ts, and then we have got a T infinity. What is Ts? The temperature of the surface, right? What is T infinity? The free stream temperature. And what is T? And what is T? T is this thing. T is the temperature of the fluid at any y, at any y. For example, at this y, or at this y, or at this y, or at this higher y, or at this higher y. So T is in fact the temperature of the fluid as we move in y direction. See what happens when we are closer to the boundary layer end. The temperature would approximately be the same as T infinity, right? The temperature in this region where the boundary layer is ending would approximately be the same as T infinity. So Ts minus T infinity over Ts minus T infinity would approximately be equal to 1. So this is what is written over here. So if we are closer to if we are closer to the end of the boundary layer, this ratio would approximately be 99% or approximately be 1, right? Because at the end, after the boundary layer ends, T becomes T infinity. So when T becomes T infinity, this ratio would become 1. This ratio would become 1, and when we are just before the boundary layer, so this ratio would be approximately 99%. Now this expression is regarding Q, heat transfer. But in fact, if you take a look at it, you will see that it is heat flux. So it is Q by A. And on the right hand side, we have got a negative sign, and then we have got a K. So if we take this area on the right hand side, it would become minus Ka, and then delta T by delta X or delta Y. So what is written over here? It is nothing but the Fourier's law of heat conduction. Minus Ka delta T over delta X. Since it is written in Y direction, so it is minus K times A times delta T over delta Y. Now how it is written? What does this mean? Over here Kf refers to the thermal conductivity of the fluid, because fluid is getting heated up, fluid is getting energy from the plate. So it is minus Kf, where Kf represents the thermal conductivity of the fluid. This is the expression for conduction. Kindly remember that the very first layer of the fluid, which is in direct contact with the surface, would have the same velocity as that of the surface, and the heat will be transferred via pure conduction to the very first layer of the fluid, which sticks to the surface, no slip condition. So that is why you can see that when it says dou T by dou Y, it is being evaluated at y is equal to 0. What is meant by y is equal to 0? At y, what is the point where y is equal to 0? It is this point. Means it is the liquid solid surface interface. It is the liquid and solid surface interface. So at this interface, where the liquid sticks to the solid surface, or the very first, or you may say that the heat will be transferred from the surface to the very first layer of the fluid via pure conduction. And this is why we see minus K of the fluid times the area, and the area has been taken over here in the denominator of Q, and that is why we are calling it heat flux. and we have got delta t over delta y, and this dou t by dou y is being evaluated at y is equal to 0. You may call it dt over dy as well, or you may call it dou t over dou y. I have explained the difference between d and dou earlier regarding partial differentiation. Now, before I move on, if it is Q, it is heat in watts. If it is Q double dash, it is heat flux, means Q by A. And some of the times we will also come across Q by L, heat transfer per unit length, and we represent it with a single apostrophe, Q dash. So Q watts, Q dash means Q by L, Q by length, watts per meter, and Q double dash means Q by area, means heat flux in watts per square meter. Now the heat transferred via convection. If you recall, heat transferred via conduction was given by Fourier's law of heat conduction, which said that Q is minus Ka delta T over delta X. Now the heat transferred via convection is given as Newton's law of cooling, and it says that Q is HA delta T. So the Qs is the heat transferred via convection from the plate to the fluid, or from the fluid to the plate, depending upon if Ts is greater than T infinity or vice versa. A is the area of the plate from which the heat will be transferred to the fluid, or from the fluid to the plate. Ts is the temperature of the surface, and T infinity is the temperature of the fluid. If we are writing it in this form, Ts minus T infinity, so Ts would be greater than T infinity, or if it is other way around, we may write it as T infinity minus Ts. So then the heat will be transferred from the fluid to the surface. So all the things are pretty much clear. A is the area, Ts is the temperature of the surface, T infinity is the free stream temperature of the fluid. The last thing is H. H is what we call convective heat transfer coefficient. Convective heat transfer coefficient. Just like we had a K in the conduction expression, we have an H in the convection expression. However, K was having the units of watt per meter Kelvin, but the units of H would be watt per meter square Kelvin, or watt per meter square degree Celsius, because Q would be in watts, area would go into the denominator of Q, so it would become watt per meter square, and then delta T in Kelvin or in Celsius will also be in the denominator of Q. So H would have units of watt per meter degree Celsius or watt per meter Kelvin. Kindly note that thermal conductivity was a material's property, but H is not a material's property. H is heat transfer, convective heat transfer coefficient is not a material's property. Why is it so? It is so because this convection heat transfer depends upon so many parameters. Let me give you a very simple example. Consider two cases. Case 1. We have got a fluid, we have got the plate at 100 degrees Celsius, and the fluid at T infinity of, let's say, 30 degrees Celsius, and the fluid which is moving is air, and say it has a velocity of 1 meters per second. Now consider case B, where we have the same plate at same temperature of 100 degrees Celsius and the same fluid, which is air, at the same temperature of 30 degrees Celsius, but with a different velocity. Of, let's say, 5 meters per second. Previously it was 1 meter per second, in case B it is 5 meters per second. So the plate is the same at the same temperature, the fluid is the same at the same temperature. The only thing that varies between cases 1 and 2 is the velocity of the fluid. And as per our previous discussion, since the fluid is having higher velocity, so the velocity, since the velocity is higher, it will end up in higher convection heat transfer. So what did we change? We did not change any material. We did not change any material's property. All we changed was the velocity of the fluid. The velocity is not really a material's property, right? So we only change the velocity of the fluid. We change the convection heat transfer rate, and it depends upon other parameters as well, such as the K of the fluid. The convection heat transfer rate depends upon the K of the fluid. For example, if we keep the velocities of the fluids the same, but we change the fluid itself. For example, if we have K of 0.01 and another fluid with a K of 10. So in this case, since we have kept the same velocities, but we have changed the material, we have changed the fluid. So even then, the heat transfer would change, because the material having higher value of K would be able to take away more amounts of energy as heat. Would be able to take away more amounts of energy as heat from the plate if Ts is greater than the infinity. So since H depends upon so many parameters, so it cannot be a material's property. It cannot be a material's property. Rather, H depends upon, I had shown you earlier, that H depends upon a lot of parameters such as the fluid velocity, the thermal conductivity of the fluid, the viscosity of the fluid. Of course, you can find out the effects of the density or the viscosity, the effects of viscosity on the heat transfer or on the velocity. Because if it is more viscous, then it would have a different velocity profile, and if it is less viscous, it would have a different velocity profile, etc., etc., etc. So since the heat transfer rate, the convection heat transfer rate depends upon so many parameters, H cannot be a material's property. It depends upon some material properties such as the viscosity and density and thermal conductivity and specific heat, but it depends upon velocity as well. So K is a material's property and H is not a material's property. This is the same thing that we have discussed. The last thing before we end convection are some values of H. See, in convection heat transfer, a major job is to find out H. The major job is to find out H, and this is what we would be doing for almost all the time in convection. We would be having various cases such as the fluid is flowing over a surface or through a cylinder or outside a cylinder, etc., 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 and then we will be finding out the values of H for various cases. However, see what we are being told over here. We are being told that for the free convection in gases, H would vary between 2 and 25, and in liquids it would vary between 50 and 1000. So what we are learning? We are learning that H in liquids would be more than H in gases. Heat transfer coefficient would be more, and ultimately the convection heat transfer would be more in liquids than in gases. And if you can figure it out, or if you can recall that we have got air cooled condensers and water cooled condensers, right? And water cooled condensers are more efficient, you can say, because they are able to take away more energy. Why? Because it is water, right? So water has got a higher value of specific heat. Water has got a higher value of specific heat. Remember, there was a Cp over there as one of the parameters that convection heat transfer and convection heat transfer coefficient depends upon. So water has got a Cp of about 4.18 or 4.2 kilojoules per kg per Kelvin, whereas gases such as air has got a Cp of 1.005 kilojoules per kg per Kelvin. So what does this mean? If air has got a Cp of 4.2 kilojoules per kg per Kelvin as compared to the Cp of air, which is 1.005 kilojoules per kg per Kelvin, so it means that the water can absorb 4 times the energy as the energy absorbed by air, and in order to bring unit degree Celsius change in temperature. Because by definition specific heat is the amount of the energy that would be absorbed, for example, by a fluid to bring a change in unit mass by 1 degree Celsius or 1 Kelvin. So where there are liquids involved in heat transfer, so they would be able to take away more energy, to absorb more energy, to convect more energy as compared to the gases. And what are we learning between these two? What are we learning between these two? Free convection and forced convection. See, in free convection, gases H is between 2 and 25, whereas in forced convection, H of gases is between 25 and 250. So we are learning that in case of forced convection, the heat transfer would be more if we compare the gases. Right? And if we compare liquids over here, in case of free convection, liquids have an H between 50 and 1000, whereas in case of forced convection, liquids have an H between 100 and 20,000. It means that if we compare the liquids, so the liquids would be able to convect away more energy if that is the case of forced convection than in the case of free convection. So we are taking away two things from here, 2 points from here. Liquids will result in more convection heat transfer than gases, number one. Number two, forced convection would result in more heat transfer than free convection if we are comparing gases with gases, or if we are comparing liquids with liquids.